To the post-lunch session on quantum cryptanalysis. And the first talk is on reducing the number of qubits in quantum information set decoding, and it will be presented by Andre Schottenhofer.
Thank you.
Please start.
So how's the sound? Looks good. Okay. So thanks a lot. I'm very happy to be here. I'm going to present this work, which is joint work with Clémence Chevegnard and Pierre-Alain Pouc on quantum information set decoding. Okay, I'm going to jump in very quickly and already into the problem that we're studying, because it's quite standard, and I'm not doing anything very complicated in code-based crypto here. So a linear code, it's a dimension k subspace of a vector space. Here it's on F2, so F2 to the n. And we specify it as a kernel of a parity check matrix. So the parity check matrix has dimension n minus k times n. You can imagine that n and k are the same order. And we are studying the problem to decode a syndrome. So we sample an error vector, which has a small number of ones, small Hamming weight. And we get the syndrome, which is h times e. And the goal is to find e. Basically, and this will be the most of code-based crypto that we'll see in this talk, the security level of code-based crypto systems depends on the generic complexity of this syndrome decoding problem. There is a very nice algorithm to solve it, and that's branch algorithm. And this is the first of the family of the ISD algorithms. There are many more which came after, but for some reason we'll be most interested in branch, which happens to be the simplest one. And the idea is to guess the positions at which the ones in the error vector E are going to appear. So imagine that you define the subset of all possible choices of n minus columns among the n columns of H. And that would be the subset, the set S and K. And if you rewrite this equation like this, H times E as a linear combination of columns of H. You can notice that if you select a subset of n minus k columns, and it happens that all the errors fall in this subset, then you can directly invert the submatrix. And you get a vector which has weight W, and you can recognize this as a good choice of the columns and already find the error vector. So the idea is to find this right subset of columns. You get a submatrix which is square, so you can invert it, and you can directly obtain, you can invert it on the syndrome and obtain the good error vector. So this is very simple. The complexity of this algorithm is well known, because it just depends on the number of errors and n of k and n on k. So if you take a random choice of columns like this, your probability to succeed is this one, and then your time complexity. After repeating this a lot of times, it's basically 1 over probability to succeed times the cost of linear algebra for the inversion part. Now, there are many improved algorithms, which is why this talk is actually going to be on very simple algorithms, because all these improved algorithms basically put less constraints on the choice of columns, and they have less loop iterates to perform. But this comes at the cost of doing more computations at each iterate, and usually this means more memory. And in this talk, we're interested in memory-efficient algorithms, so reducing as much as possible the amount of memory we use. So all of these advanced variants, they're out of the picture, and we're only focusing on the simple initial branch algorithm. Because we're going to make it into a quantum algorithm, following the idea by Bernstein at Crypto 2010. And the idea is simply that you can speed up this search for a good subset of columns using Grover's algorithm. And this will be like the quantum slide of this talk, although in the quantum cryptanalysis session, actually, I tricked you into attending a talk about classical circuit optimizations. So the quantum part is simply using Grover's algorithm, and Grover's algorithm simply needs to have an algorithm that samples a search space and an algorithm that tests if the element you sampled is good or not. In our case, sampling a choice of columns is usually fine, and testing if the choice of column is good, this is the inversion part. This is where you compute the submatrix, invert it on S, and check the weight. And this gives you already, this tells you with certainty if you choose the column well. And this is the part that takes n cube bit operations to take the terms of Bernstein. And there are also improved algorithms, just like there are better classical algorithms. But again, they follow the same principles as the classical algorithms, and so they're going to use more memory. So we're not focusing on that either. If we want to optimize Grover search in our case, and if we want to optimize the quantum ISD, we have to focus on the test. Because it happens that the testing operation, the moment where you decide if your choice of columns is good, this is what contains most of the cost of the circuit, both in space and in time. The rest is not dominating. And in our case, and the reason why I'm not actually very much talking about quantum algorithms in this talk, which is about quantum algorithms, in our case, the test can be described as a classical circuit. So what happens is that usually quantum algorithms are described as quantum circuits, and these quantum circuits only describe a sequence of operations as a circuit. And in our case, we have a purely classical operation to apply. This operation is simply determining if an input choice of columns is good or not. So this is a purely classical algorithm that we compute, and we can compute it with a purely classical circuit. But due to the rules of quantum computing, this classical circuit has to be reversible. So if we do it like this, usually you have your input, and you write the result in an output that you initialize to 0. This is reversible because you can typically apply all the operations in reverse and return to the input that you have. So this is a kind of thing that we want to do. And this circuit for the test, and this is where an issue arises, this circuit for the test needs n cube operations for Gaussian elimination, and it needs around n squared space to write the submatrix that we're inviting. But n squared is large. In ISD, n squared is going to be around millions of qubits. So in this work, what we propose is a new trade-off where you can really minimize the number of qubits that you need in this operation. So initially, we would have had a circuit where you needed n squared space, so n squared qubits, that's really large. And it would have around depth n, and you would basically take n cube gates. So the new circuit has also n cube gates, we're not moving that, but it will reduce it down to n space, bigger than space. And there are also different trade-offs possible, and one of them is also interesting because the space is slightly suboptimal, but you get asymptotically less nonlinear operations. And minimizing nonlinear operations is very important in quantum circuits. Okay, so now I can present the main idea. And the main idea is going to take me only 3 slides because it holds in one sentence. This is using Wiedemann's algorithm for inverting the matrix. So recall that what we're doing here is simply performing an inversion circuit where the matrix to invert is given implicitly. It's given by the choice of columns in the ISD routine. And if we have a matrix and is given implicitly, or in our case only by matrix vector products, Wiedemann's algorithm allows to invert this matrix on a given input. And so this algorithm will only use a black box for a matrix vector product. And the idea is really nice. Assume first that the matrix is invertible. This happens with constant probability. You consider the space spanned by all the iterations, the powers of this matrix Hi applied to S. And you know that there is a minimal polynomial. So there is a minimal P such that this cancels, so P of Hi times S equals 0. And so you can verify that if you take the shifted polynomial, this polynomial is monic, so we replace the 1 and then you shift the coefficients. And you apply this to Hi and multiply by S. This is the inverse. This is the element you're looking for. So the strategy is find the minimal polynomial and then evaluate it. And we can reduce this problem to a linear recurrence in F2, which is more convenient, because you can just take a random vector and project using this random vector. So now you get just a sequence of bits, and you have to find the minimal polynomial. And then this will eventually give you the inverse of the matrix. So the algorithm is a bit more complicated than that, because to get to constant probability of success, you actually need to iterate this. But I'm just going to give the broad overview. So you choose a vector, which is actually not random, but fixed. You compute this sequence, where you iterate, you take the powers of the matrix, apply it to S, and you project it. You compute the minimal polynomial, you compute the shifted polynomial, you evaluate it, and you get the inverse. When you get something, and with constant probability, this something is inverse, and it's quite easy to test, because you can just multiply by the matrix and check that this works. So the fact that it's easy to test is also nice for the algorithm. And what I just have to convince you now, and the only remaining part of my talk, is that all of this that is on this slide is doable reversibly, so without losing any information at any point, and in big O of n space, because that's the point of what we're doing here. So minimize the amount of space that we need. And so although the matrix itself, the matrix Hi, is of size n minus k times n minus k, so big O of n squared, you can do everything, all of these operations, in linear space. So I'm going into some details for the circuits, just to give you a few hints, a few ideas of how all of this works. So we have 3 steps, but we also have another one, which is the matrix vector product. So we do have to implement this part, and we cannot implement it like this. You cannot multiply the input by the matrix and obtain the product, and the reason is that we're doing reversible circuits. So if you were able to do this, you also would be able to invert the matrix, because you could go backwards. And this is what we're trying to do here. So there is no hope to do that. What we can do for the matrix product is something a bit different, where you take an input and then you XOR your output, so the matrix product HIX, into a new register, another one. This is something that is doable. At least it's reversible, because where the reverse of the circuit is simply the same circuit. You can go backwards, and it gives you back, it's involutive, it gives you back the register Y. So that is what we're trying to implement. And there are different possible trade-offs, which lead to the different possible complexities that I gave. But the general idea is simply that if you take your input vector x, and you expand it by adding some zeros, you will get a vector where all the coordinates of x are placed correctly, so that the hi times s is equal to h times this expanded vector. And h, it's a constant matrix. It's the input of the problem. So the multiplication by h is simply a linear circuit that is very easy to implement. Basically, you can imagine that h, all this information, it's built in the circuit. So you still don't need much space, because you don't need to write it down in space. So I'm not detailing all of this, but this is where different trade-offs happen, and you have different choices depending on how you represent the choice of columns I on the cost of this operation. Okay. The other step, the next step, is to evaluate the sequence. And there is a problem with the sequence, is that it involves the powers of the matrix H. But we can't compute directly the product in place. What we compute instead is the product in a new register. So if we iterate this, you see that this looks more or less like a Feistel scheme, right, for symmetric cryptographers. But also that you don't obtain the powers of H. You obtain some polynomials of H applied to your initial vector. But this is fine, because these polynomials, they also form a polynomial basis. So actually, every power of H is also a sum of these polynomials of H. And so you can evaluate the sequence indirectly by evaluating the sequence of polynomials and then taking the values when you need them and storing them into a new register. So you can do all of this still in big O of n space. And you can evaluate the entire sequence by going through the polynomials, these polynomials that we have. The second step is to compute the minimal polynomial of a sequence, and for this we use the Berlekamp-Massey algorithm. Can you do that reversibly and with linear space? The answer is yes, but that wouldn't fit into a single slide. So you have to trust me on this. The nice part is also that this part here is non-dominating because the complexity is only quadratic and the entire complexity of the algorithm is qubit anyway. So, so barely compensate is fine. And finally, there is a third step, which is to evaluate the polynomial. So a polynomial which is not the minimal polynomial, but the shifted one, which is supposed to give you the inverse. And evaluating a polynomial, again, we fall in the same problem that we don't have direct access to the powers of the matrix. We only have this intermediate polynomial basis. But this is going to be very similar to the sequence evaluation. And it works in a very similar way. The polynomial of hi applied to S is equal to a linear combination of the polynomials pi applied to S. And so you can do it in the same way. And it happens that the entire algorithm is dominated by steps 1 and 3, by the evaluation of the polynomials. And steps 1 and 3 themselves, they are entirely dominated by matrix vector multiplications. So everything goes back to how we implemented this implicit matrix vector product, and this is where we have different trade-offs possible. So I'm going to move to the conclusion part of the talk, which would be a quite long conclusion, because I want to present just an example. So the example would be classic Michaelis level 1. So as I said very briefly, the numbers are large. So the size of the matrix is, so the k is equal to 2,000 and the n is equal to 3,000. This gives you basically, if you want to represent the entire submatrix and invert it, you need 4 million qubits. So these numbers for the Gaussian elimination circuit, they were computed by Periello et al. And they also computed to do the 30 gates, which is quite large. This is already what you need when you run Shor's algorithm, and in this case, it's only a single iterating Grover's algorithm. And if you factor in the number of iterations you need, in total, Grover's search would require to be 100 gates, which is very large. So there are different versions, as I said, of our circuits. The one that optimizes at the most possible space falls to 18,000 qubits. And the number of gates is slightly larger, and this is because of the big O. The asymptotic complexity is the same, but the constant of the big O is not really nice, I'm afraid. And so it actually increases the number of gates. And if we look at the version optimized in nonlinear gates, the number of qubits is larger, and then the number of gates is a bit smaller. We have better constants in general. And finally, there is yet a third version, and this is when the matrix has a special structure, because in code-based crypto systems like BIKE and HQC, the matrix is block circulant, and implementing a matrix vector product in that case is asymptotically better. And there we can really use the advantage that's given us by Widman's algorithm. So, to conclude, we certainly understand that we didn't break code-based crypto, and that was expected. The only thing that changed here is that before, if you wanted to run Branch's quantum version, you would have a qubit count basically infeasible, millions or billions, and a gate count infeasible. And now what you have is a gate count that is infeasible, but at least the number of qubits can become similar to the one you find in Shor's algorithm for large RSA variables. The other thing is that this circuit is not specific to code-based crypto, actually. We're just inverting a matrix. So this might be useful in other quantum cryptanalysis algorithms, even though this paper is focused on the code-based applications. So you can find the paper on ePrint, and we also implemented everything, all the circuits described here, to check the counts, and so this code is also on the web. Thanks a lot.
So any question from the audience? Yes.
Hi, thanks for the talk.
Oh, sorry.
Andre. In practical ISD for crunch, I think you would often not sample your information set fully random every time. you would only like swap in or out a constant number of coefficients, maybe. Would that also work for your case and like reduce the complexity to quadratic instead of cubic?
Yes, so this is actually related to some optimizations that are still possible, I think. So initially in the quantum setting, we start with, okay, we can, if we can sample the choice of coordinates at random, we understand nicely how it works. But indeed, you don't need that much entropy, even in the quantum search. So you could have a different algorithm which doesn't sample really exactly a set of coordinates at random, but simply something that is good enough. And this is not something that we did, but I think it would largely improve the algorithm. It wouldn't make it quadratic because you still need to invert a matrix at some point. That's still, it would be, I don't know, it would be a bit better. And that's especially, I'm talking here of the Toffoli optimized version, so the version optimized in nonlinear gates, because this one really depends on how you represent the choice of coordinates. Yeah, without more details, but that's related to that.
Any other question? Yeah, so I have a quick one. So the gate count, as you know, the complexity class does not change, but you know, by sacrificing some more qubits, because you're reducing the qubits drastically anyway, is it possible to play around with the constants?
Yes, a bit.
Mm-hmm. I mean, did you try that, or maybe it's a possibility that you want to look at later?
So for me, the best trade-off seems to be optimizing the second version here, because right now and that's related to what I said to Vessel. That's the space complexity is asymptotically n times log n squared, and that's because n times log n squared is the number of switches you have in a sorting network. But if you reduce this and if you do it more heuristically, you could reduce it, like, I don't know, to n log n perhaps, and that would be much better in space. And then if you're much better in space, then you don't have any incentive to use the other version anymore. And now you get better gate counts and better constants.
Okay. Okay, that makes sense. So if there are no more questions, let's thank the speaker again.
I mean, he's here. He's in the wings.
Okay, so the next talk is on the semi-direct discrete logarithm problem in finite groups, and it will be jointly presented by Christopher and Giacomo.
Well, thank you very much for the introduction, and more generally to the organisers. It's exciting to be here in Kolkata. So myself and Giacomo are going to talk about the, I suppose, completion of a program of cryptanalysis to do with a plausibly post-quantum problem called the semi-direct discrete logarithm problem that lies somewhere outside the kind of standard NIST stuff. You'll notice also that there's an unusually large number of authors here. This is mostly because we all met at an American Institute of Mathematics workshop, and so we'd like to thank them as well. So I'm going to tell you what the semi-direct discrete logarithm problem, or henceforth SDLP, is, and I will talk about how you can reduce it to simpler cases, and then Goutam is going to tell us about how we can solve those simpler cases. This is a whistle-stop tour of what SDLP is, which is a field that's been going on for about 10 years now. But for our purposes, we care about what happens when we take finite group G and its automorphisms, and we look at pairs of group elements and automorphisms. And we can equip these pairs with a multiplication that has this nice twist in the first component. So we're applying the automorphism to H before we multiply. And the sort of game of semi-direct products cryptography is you keep taking powers in this semi-direct products group, and you can see that you're going to get these strange-looking products in the first component. So somehow you have a non-abelian version of the discrete logarithm problem, because even though you've got some cyclic structure going on upstairs, if you choose your G to be non-abelian and you're projecting down, you might hope to avoid standard reductions to short period finding routines, for example. And so the game we're going to play is, say, I'm going to give you an element that looks like one of these weird long products that I promise you is of that form, and you have to decide which integer produced it. So it's, in that sense, an analog of the discrete logarithm problem. To introduce some notation to any choice of pair in this semi-direct products group, I'm going to define this function rho that such that rho applied to H is G times phi applied to H. It's not hard to see that if I keep applying this thing, I'm going to get the products that I was talking about. And so basically we can cast SDLP as an orbit problem, although again I should disclaim that this is a recent strand of the literature. I want to get into the technical meat of it, so I won't give you too much of a history. And you can define SDLP as an orbit problem exactly as you'd expect, right? I mean, you're given a group element that you're promised is the evaluation of some rho that you know on the identity. And the semi-direct discrete logarithm problem is to work out how many times you applied this function. And notice also that this is defined for any group, right? So there's like a large variety of problems that we could get. Why do people study this? Well, I mean, I hope I've argued at least briefly that it's not trivially quantum vulnerable. I mean, there's at least some work that goes on here. It's quite a natural thing to think about, and in the spirit of this recent NIST drive to boost the diversity of the post-quantum roster, it's also nice that it exists outside the mainstream. Actually, it's known that this thing occurs as an example of a commutative group action, the most famous cryptographic example of which is the Seaside action, and the same as them we get these things like Diffie-Hellman-style key exchanges, which are nice. There's not many of those in the post-quantum landscape. Digital signatures that are appealing in some sense that I won't go into. Closer to the spirit of this work is some recent cryptanalytic work, in particular the work of Mohammed Imran and Gabor Evanios that appeared as an e-print at the back end of last year and was published this year. And this is this sort of recursion to simpler examples. So the intuition here is that if we can somehow trap our instance of SDLP in some arbitrary group G in a normal subgroup, then we're allowed somehow to take this trapped problem out and solve two smaller instances of SDLP, such that solving these two smaller instances suffices to give you a solution in the larger group you started with, which immediately suggests some kind of recursion, right? Because, I mean, your instinct is going to be like, okay, well, why don't I just do that on these smaller groups, and then eventually I'm going to run out of normal subgroups and I'll output a bunch of solutions in simple groups, or I'll output a bunch of problems in simple groups. So more precisely what Imran and Evanios show is that if you have a phi invariant normal subgroup, so a normal subgroup that's fixed setwise by some automorphism, by the automorphism phi implicit in the problem, you can get solutions of SDLP and G as linear combinations of SDLP solutions in these smaller groups. And they use this to show that you can do SDLP in all the finite solvable groups, as well as some less catchy groups, basically whose composition factors are small enough linear random groups. So we complete this program effectively. So we're going to appeal to some results in computational group theory that we won't go into that much, just for sake of time. But with access to these methods from computational group theory, we can reduce an arbitrary instance of SDLP in a finite group to tractably many instances of SDLP in the finite simple groups. And because we have the classification, we know what all of those are. So we just have to work out how to solve SDLP in each of those. And that's what Giacomo is going to tell us about. So before I pass over to him, I will tell you a couple of the details about carrying out this reduction. So you need to be able to compute these invariant subgroups, which is, in other words, you need to be able to trap your problem in that little picture I showed. And also you need to make sure that your recursion is going to terminate. So one of these computational group theory tasks we're sort of outsourcing to their literature is this ability effectively to compute composition series, but for our purposes, computing a maximal normal subgroup of G, call that N. Imran and Abani show us that eventually this intersection of increasing powers of phi applied to the normal subgroup is going to terminate in a phi invariant subgroup, so this is the thing that we're looking for to continue our reduction. But of course, it might happen that it terminates in the trivial subgroup, in which case the recursion can't proceed, because if you cut out the trivial subgroup, the quotient group you're left with is just going to be the same group again, so we're not going to proceed down to smaller instances. That won't happen if the normal subgroup you started with contained a characteristic group, because the characteristic subgroups are exactly those that are fixed by every automorphism, and so your intersection can't be smaller than this characteristic subgroup. And so we have this nice result where we show that having a characteristic subgroup, any characteristic subgroup, is actually equivalent to every maximal normal subgroup containing a characteristic subgroup, which is nice for a couple of reasons. One is that we're sort of agnostic about which maximal normal subgroup we get, because either all of them will do or none of them will. But also, because of this equivalence, we get a way of detecting if we're in a scenario we have a characteristic subgroup to start with or not. So in particular, if the phi invariant subgroup we come up with is the trivial group, we must have started with something that doesn't contain a characteristic group. These guys are called the characteristically simple groups, and it turns out that these are just, it's reasonably well known that these things are just the direct product of so many copies of a simple group, and so actually the automorphisms of these things look like a sort of permutation and then application to each component. And it turns out that if we have outputted our trivial group, then we're going to be in a scenario where we have a K permutation involved in our automorphism, which means that we induce basically polynomially many SDLP instances in a simple group. So even in a scenario where we can't compute this phi invariant normal subgroup, we know we're going to be in a scenario where we're sort of fine anyway. We have a different reduction to simple groups. So the final thing to check is that this recursion terminates. The reason this recursion terminates is because of the correspondence theorem, which tells you about the subgroups of quotients. So the subgroups of quotients are those that are trapped between the two factors, basically. And so this procedure has to terminate, has to output finitely many instances of SDLP in either a simple group or a characteristically simple group, which again you could just think of as outputting instances in a simple group, because otherwise you'd have a way of describing infinitely many distinct normal subgroups of a finite group, which of course can't happen. So that's got us to where we now need to solve SDLP in all the simple groups, and at that point I'll hand over.
as Kit said, we are back to the problem of solving the problem for simple groups. But here we are lucky because like one of the major results of 20th century mathematics is this big theorem called like classification of finite simple groups that tell us that there exists essentially a finite list of possible parameterized families of simple groups with well-known characteristics, and every finite simple group needs to be isomorphic to one of these, or is one of 26 so-called sporadic groups that we know they are classified. And so like what we can do now, since we know that SDLP essentially reduces to the problem of being solved on finite simple group, just focus on this list and try to go through to the list and see what we can do. And essentially we concluded that it's not possible to build some kind of secure post-quantum cryptography based on this problem, because neither of these elements of the list is deemed to be secure against quantum cryptanalysis. So let's start immediately with a warm-up example that is the first item of the list, so cyclic groups of prime order. And for them, like, it's just a warm-up, but it was clear from the start that they were not secure. And the observation is quite simple, like, since we are in cyclic groups, the automorphisms need to be exponentiation. And so doing the semi-direct exponentiation is essentially equivalent to doing the classical exponentiation for finite fields, just with a geometric series we did. So you can just apply essentially the Shor algorithm to solve discrete logarithm 2 times, one to recover the geometric series, and one to solve find the exponent in the geometric series. So, like, no abelian groups to consider. Let's try to track the others. And for this one, okay, we have to combine several existing results and to solve them. And first of all, we just focus to the case of linear groups, since the remaining families are, most of them are linear groups or projective linear groups. And suppose we have a group of matrices, and we are just considering an automorphism that is inner. That means it's a conjugation, so a multiplication on the left by one fixed group, and on the right by the inverse of this fixed group element. And in this case, it was shown in this paper, in Ram and Livanos, that essentially the problem, by using the vectorization of these matrices and some tensor product, essentially reduces to this discrete log-looking problem called the matrix power problem. And in fact, this problem is well known to be solvable, essentially reducible to discrete logarithm on the space of matrices, on a different space, but still, like, it's just a discrete logarithm computation. And so, if we are in this setup, the problem is easy. And also, if we are even considering projective linear matrices, the problem is still easy. You just need to be careful with the parameters, but we show that it remains easy. So, okay, the only catch here is that we need to consider inner automorphism. However, this is not a problem, since we know that we just need to focus on non-abelian simple groups. And for this, there is a result from 20 years ago that tells you that if you have an automorphism of a non-abelian simple group, you can just compute the exponent of it by a small power that is smaller than the logarithm of the cardinality of the group, and then you will get an inner automorphism. And then we just need to combine this with another result for the Iram and Ivanov paper, in which they show that if you can solve semi-direct discrete logarithm problem up to a small power, that in our case would be let's say the value x that cannot make it work. However, if we can solve it up to a small power, then we can solve it for the automorphism which we started, and that means that combining this result, essentially we can solve the semi-direct discrete logarithm problem in any linear group. And luckily, like all of these three infinite families are linear groups or projective linear groups. And so we can solve them if we have them in a standard representation. However, there is to say that this is not enough, because it would be like saying that since discrete logarithm problem is easy on the modular integer, then it's also easy on elliptic curves. That clearly is not true. You need to compute the isomorphisms between groups. So we need to put ourselves in a slightly more generic situation. And the model we use is called the black box group model, that essentially you suppose that you have a group with some oracle that will compute for you the multiplication, the inverse, and the comparison between elements. This in some sense resembles the generic group model that probably you know for elliptic curves. And it is to say that, okay, it clearly justified to be used in a cryptographic context, but this generalization of groups, we did not invent it. We found it in computational group theory literature, and inside computational group theory literature, there is a branch of them that focuses on a particular problem called the constructive recognition problem. That is essentially the problem of starting from a simple groups, finite simple groups, represented as a black box group, and try to compute efficiently an explicit isomorphism to a standard representation. That for us essentially means compute a linear representation of this simple group. That would immediately imply, with the previous result that I recorded on linear groups, that we can solve semi-direct discrete logarithm. In the paper, we will go a little more in detail with all the commutative diagram that you need to use, but they are pretty straightforward. And so what we need to do is just essentially to go down through the results in this part of literature and see if we can apply them. And the answer is yes for most of them. Essentially for alternating groups, this is pretty straightforward. You can even compute this explicit isomorphism in polynomial time. You don't even need a quantum computer. For classical groups, it becomes a little more complicated because they showed it to be possible, but they need some kind of oracle, access to some kind of oracles. However, these oracles are essentially what they call number theory oracles that are quantum computers, because they are just discrete logarithm oracle and factoring oracles. And then they need to have an oracle that will solve you the problem on a small class of two-dimensional matrices. And also, this kind of oracle can be constructed or for quotient of metric groups that are broader class of black box group, or if you have a discrete log solver, you can even construct them for any black box group. This is a relatively recent result. And since we are in the quantum cryptanalysis area, this is not a problem for us. We can assume to be solvable. And so we just need now to focus on exceptional Lie groups that are just some Lie groups with some peculiar structure. And also for them, there are a lot of results on computing this explicit isomorphism. Essentially, we found results in all of them, but for two exceptions, that are the large Lie groups, the 2F4, and the Steinberg groups, 3D4, but just for even characteristics. And so the problem is solved for all of them, but these two. And so we can solve semi-direct discrete logarithm problem on all of them. On these two, there is to say that as of now, there is no public result on them. But if you read through the paper that solved the problem for the other, they explicitly say that they expect the strategy they use to work also on these two exceptions. And also, we asked to people working on this kind of stuff, and they told us that they expect them to be done in even people are already working on this, and however, they don't expect them to be a particular problem. They are just missing up in the literature to be solved. And so, for all these infinite families, it is solved. We just need to solve the problem then for sporadic groups, and that are a very limited example. And I'll go quick since we have little time. But the point is simple. Like of these 26 sporadic groups that we know, there is only one who has like cryptographically acceptably sized. That is the well-known monster group. While all the other are like or some quotient of the monster group or too small for cryptography. And however, even if this cardinality would be okay for cryptography, first of all, we can generalize by every step giant step algorithm and solve it in square root of time. But also, like if we look closer to the baby step giant step parameters, we see that essentially the limit is much smaller because like we can just limit ourselves as a complexity to look for the product of the maximal order of groups and automorphisms. And essentially, if we compute this invariant for all the sporadic groups, the maximum we can get is like 15 bits of security, both for monster group and parias and other groups. And so essentially, we concluded that it's not possible to get a secure similarity discrete logarithm problem in any of the simple groups.
Okay, thanks for the interesting talk. Let's thank the speaker. We have time for a couple of quick questions. So any question from the audience? Okay, so maybe you mentioned, but I would ask again if I missed it. So what is the best complexity to solve the constructive recognition problem? Like the constructive recognition problem for the group isomorphism that you mentioned.
What's the question?
What is the best complexity to solve the constructive recognition problem? Like for the black box group, and then there is an explicitly specified group, if there is any isomorphism between them. You referred to Babai's 2009 paper, right? So what is the best complexity?
The base complexity. What do you mean by base?
The best.
Okay, sorry. Honestly, I don't know. They are just polynomials. That's in the system parameter. That's what they said. I remember some cubics in the polynomials, but honestly, like I haven't. Like I was fine with knowing that they were polynomials.
No, that's okay. So if there are no more questions, let's thank the speaker again. I mean, both the speakers. Okay, so the next talk is on quantum algorithm for first correlation attack on LFSR-based stream cipher, and it will be presented by Akinori Hosoyamada.
Thank you for introduction. I'm Akinori Hosoyamada from NTT Secure Platform Laboratories. And today's my talk is about quantum algorithms for fast correlation attack on LFSR-based stream ciphers. And so firstly, I'd like to give a brief summary of this talk. In our paper, we showed some quantum algorithms on fast correlation attacks by relating classical fast Fourier transform or its special version, fast Walsh-Hadamard transform with quantum Fourier transform or its special version, Hadamard operator. And in the setting of Q1, it seems hard to achieve meaningful speedup. But in the setting of Q2, by introducing some new special attack model, we observe an interesting speedup by using Schwartz algorithm for discrete log. And the complexity in the setting of Q2 is order L to the 4 over C to the 2. If the length of LFSR is L bit and a linear approximation of correlation C is available. And we applied our algorithms to some ciphers. And we observed the first quantum attack on SNO2 that is faster than global search. And also the current best quantum fast correlation attack on SNO3G. And so, yes. And next, I'd like to explain some backgrounds in the quantum setting and the motivation of our research. So when studying quantum cryptanalysis on symmetric key cryptography, we can consider two settings, Q1 and Q2. In the first setting, we assume that computers are quantum, but keyed oracles, I mean the encryption and decryption and PRF, these oracles are the same as the classical oracles. And in the Q2 setting, we assume that both computers and keyed oracles are quantum. I mean, quantum superposition queries are allowed. And in this setting, some devastating polynomial attacks are possible. And some previous works showed the even Mansur cipher and foreground Levy-Rakov and some other constructions. These are proven to be secure in the classical setting, but completely broken in polynomial time in the Q2 setting. And also some important Q1 attacks are based on Q2 attacks. And so here I'd like to claim that studying Q2 attacks is as important as studying Q1 attacks. And next, I'd like to explain some recent topics in the area of quantum cryptanalysis on symmetric key cryptography. So in the classical setting, there is a very strong relationship or deep connection between Fourier transform or its special version, Walsh-Hadamard transform, and some classical cryptanalytic techniques or notions, such as linear correlations or some techniques about key recovery of block ciphers. And some recent papers tried to connect them with quantum Fourier transform or its special version, Hadamard operator, by using some techniques like the state preparation or the subrouting of Simon's algorithm, and so on. And they showed some quantum speedups for linear cryptanalysis. And so this is some recent topics. And after seeing this situation, we had this research motivation. So first, there is a cryptanalytic technique which is called fast correlation attack, which is one of the most important attacks on LFSR-based stream ciphers. And many fast correlation attacks also utilize fast Walsh-Hadamard transform. And so it would be natural to ask whether it is possible to achieve some quantum speedup for fast correlation attacks by combining classical Fourier transform or Walsh-Hadamard transform with a quantum Fourier transform or Hadamard operator. So this is the motivation of our research. And next, I'd like to review the basics of LFSR-based stream ciphers. So usually, the cipher looks like this. It consists of LFSR and some additional registers. And the encryption process consists of initialization, key stream generation, and encryption. In the initialization phase, the cipher takes master key and IV as input and update the internal states many times, like this. And then, after all, the state is called the initial state. And I'd like to call this part O. It doesn't look. So the initial state of LFSR has S0. And after the initialization, it generates a very long key stream. So it first outputs a key stream bit Z0 and updates the internal state again. And it also outputs another bit Z1 and updates the state again. And it iterates such operations many times, like this. And finally, to encrypt the message, it just adds the key stream bit to message. I mean, the cipher text is the addition of message and the key stream. So this is how LFSR-based stream cipher works. And next, I'd like to review very, very basic things about fast correlation attacks. So actually, there are many variants about fast correlation attacks, but here I'd like to focus on a very basic variant. So first of all, I'd like to introduce an alternative view of this cipher. So because LFSR also produces very long sequence, we can assume that the cipher generates some LFSR sequence S, and also it also generates some kind of noise. And then the key stream bit Z is obtained by adding the noise with the long LFSR sequence. Okay, so this is the alternative view. And by introducing this, we can see that this part, the production of LFSR sequence is the encoding of the initial state of LFSR by a linear code. And this part is regarded as a code word of the code. And this part can be seen as the binary symmetric channel or some noisy communication channel. And the key stream can be regarded as the result of the transmission through the noisy channel. And the idea behind the first correlation attack is if the noise is not too strong, or the linear correlation between the LFSR sequence S and the key stream bit G is large, then the initial state S0 can be recovered by performing some most likelihood decoding. And so next I'd like to explain how the most likelihood decoding works by using fast Walsh-Hadamard transform. So here I'd like to assume that the LFSR is L bits long and we have N bits of key stream. And G is the encoding matrix and Gi is the ith column of G. And I'd like to define some function psi like this. And then some analysis shows that the Walsh-Hadamard transform of this function psi is proportional to the linear correlation of xg and the key stream z. And this value, linear correlation, becomes large if and only if x equals the initial state. And by using this observation, the decoding algorithm proceeds like this. Firstly, it collects the key stream z, and then computes and stores the value psi of w for all inputs. And then it applies the fast Walsh-Hadamard transform, and finally outputs the value x that gives the largest value of Walsh-Hadamard transform. And speaking of the complexity, the first step requires complexity n, the second 2 to the power l, and the third l times 2 to the power l, and the final step doesn't require much complexity. And the overall complexity becomes like this, and this succeeds with high probability if this inequality is satisfied. And once the initial state S0 is recovered, then the entire initial state is often easy to recover. So this is the very basic procedure. And actually, we can also mount some advanced attack if a linear approximation is available. I mean, the attack in the previous slide works in the same way if there is a linear approximation between the LFSR output sequence and the key stream Z. And after a linear transform, Z is again regarded as an encoding of S0 with some noise added. And the encoding matrix Z is given in by this equation. I mean, the ith column is represented by gamma times m something, and gamma is derived from the linear mass, and m is the state update matrix of LFSR. So this is the basics of fast correlation attack. And actually, some previous work do more complicated and sophisticated techniques to reduce the complexity, but I don't get into the details. And next, I'd like to explain the attempt of quantum speedup in the Q1 setting, where quantum computer is available, but the oracle is the classical one. And so the classical attacks looks like this. And here, I'd like to achieve some quantum speedup by replacing fast Walsh-Hadamard transform in the third step with the Hadamard operator in quantum computation. And yes, and our attack in the Q1 setting looks like this. And so in the first step, we collect the key stream Z and store it into the QRAM. This is the same as the classical attack. And the second step, each step of this attack is an analog of the classical step. And so the first step is completely the same as the classical attack. And in the second step, in the classical setting, in the second step, we computed that function psi, but in the quantum setting, we compute some quantum state that corresponds to the function, which looks like this. And in the third step, the classical third step performed some fast Walsh-Hadamard transform. But here, I would like to perform Hadamard operator. And finally, the final step of the attack in the classical setting was very simple. But here, I would like to apply some quantum amplitude amplification technique. Because here we do not have direct access to the value of linear correlation because now the correlation is encoded as quantum amplitude in the quantum state. So we don't have a direct access to the value of correlation. And so in any case, the quantum attack looks like this. And speaking of complexity, the first step requires complexity n, the second is also n, the third one is order 1. And here, there is some non-trivial thing, because in the classical setting, the third step required the complexity 2 to the power L. But here, we just only apply a single Adamar operation. So the complexity of third step is order 1. And finally, I don't explain details, but fourth step requires more complexity like this, much complexity like this. And the overall complexity is with some calculation, we can confirm that the complexity is more than this value. But here we have some problem. The problem is that the complexity is very large. I mean, for some ciphers, correlation is very small. So the first term is larger than the complexity of the exhaustive key search. And for other ciphers, the parameter L is very large. And so the second term now becomes too large. And so it seems very hard to obtain meaningful speed up in this Q1 setting. And so I would like to move to another setting, Q2. But before explaining our new attack, I'd like to introduce new attack model in the Q2 setting. So in the classical setting, a previous work showed the appropriate security notion for IV-based stream ciphers is the PRF security regarding IVs as inputs and T streams as outputs. And so after seeing this, it would be natural to think that the corresponding attack model in Q2 would assume an oracle that receives quantum superposition of IVs and outputs quantum superposition of T streams like this. But here we have some issues. The first issue is that N operations are needed only for reading output Z, T stream. And this makes the model essentially the same as Q1. And the second issue is that the quantum computer is usually small. I mean, when we consider quantum attacks on symmetric crypto systems, we usually assume that the computer is of size 2 to the power 10 or 20 or something like that. But here, the T stream can be as large, as long as 2 to the power 50 or 2 to the power 60 or something like that. And this is very unbalanced because the computer is small, but the register to only read the output of Oracle is very large. This is unbalanced and not reasonable. So I'd like to introduce a new model. And here, I'd like to allow adversaries to query not only the IV, but also the index of the T stream in quantum superposition. And I can range from 0 to 2 to the power L. This is a very strong model, but here I'd like to claim the feasibility because some stream ciphers seem secure even in this attack model. And so this is the new model, and I'd like to, I will present new attack in this model. And here I'd like to give some remarks. First, I'd like to, the purpose of studying attacks in this model is mainly to understand the power of Q2 attacks better and make a basis of other attacks in future works. And we do not claim that the practical security of cipher is affected even if it is broken in this model. And so finally, I can explain the first correlation attacks in the Q2 model. So the Q1 attack looks like this. But in the Q2 setting, we can skip this step, first step, because we have a very strong quantum oracle, and we can access all key stream bits Zi simultaneously in quantum superposition. And about the remaining steps, the third step is completely the same as before, and it requires only order 1 complexity. And with some analysis, we can show that the final step can be done with this complexity by applying the quantum counting algorithm. This is not so straightforward, but I don't have enough time today, so please read our paper for more details. And finally, this is the most non-trivial part. So in the step 2, by applying Shor's quantum algorithm, we can prepare this quantum state with polynomial time complexity. And here, sorry. And this is the non-trivial, most non-trivial part. So I'd like to explain a little bit more details. And so to prepare the quantum state psi, we have to compute this function. And to compute psi of w, we have to determine the index I such that w is equal to gi, the ith column of the encoding matrix. And this is equal to gamma times transpose of m to the power I minus 1. And gamma is derived from the linear mask of linear approximation. And m is the state update matrix of LFSR. And it is well known that multiplication of the transposition of m corresponds to multiplication of the generator element of the multiplicative group of the extension field. This is non-trivial but well-known fact. And by using this, we can conclude that gi is equal to this value. And here, the multiplication is taken in the extension field. And by using this, we can conclude that I is equal to this value. And this value can be efficiently computed because this is just discrete log. So we can efficiently compute this by using Schwarz algorithm for discrete log. And so we can efficiently compute I, and so we can efficiently compute psi, and so we can finally efficiently prepare the quantum state psi. And so in any case, the second step can be done in polynomial time, and the overall complexity becomes like this. And we applied this algorithm to some ciphers, and especially for the 256 qubits of SNO2, we observe the first quantum dedicated attack that is faster than the global search. And we also achieved some interesting quantum speedup for other ciphers. And finally, I'd like to provide some remark about concurrent and independent work. A recent workshop abstract by Einzele and Bunda also mentioned quantum speedup of fast correlation attack, but they do not explain details. So it is not clear whether or how their work is related to mine. And so finally, this is again the summary of today's my talk. We showed some quantum algorithms on fast correlation attacks by relating classical fast Fourier transform or fast Walsh-Hadamard transform with quantum Fourier transform or Hadamard operator. And in the setting of Q1, it seems hard to achieve meaningful speedup. But in the setting of Q2, by introducing some new attack model and by using Schwarz algorithm, we achieve some interesting speedup. And the complexity becomes like this. And we applied the new attack on some ciphers. And in particular, we observed the first quantum attack on SNO2 that is faster than the global search. That's all. Thank you for your attention.
Any question from the audience? Okay, we have time for some discussions. Can you go to the table, the results? Yeah. So, as in Sozamanuk, the Q1 seems to perform better, right? Compared to SNO. Yeah. Yeah, so what is the reason for that?
This is just by chance, I think. So there are many factors that affect the complexity, I think the linear correlation of linear approximation and the size of LFSR and many things. And I think this is just by chance.
Yeah, no, but in the beginning you mentioned that you can use Q2 to perform Q1 also, right? So should not Q2 be upper bounded by Q1 in some sense?
Yes, that's right. Yes.
Yeah, so that's what is something counterintuitive for me.
Because Q1 attack is naturally also Q2 attack because Q2, the attack model, attack setting of Q2 is stronger than Q1. So, I'm sorry, which part are you talking about? This?
Yeah, this part.
This one. Yes. for this part, unfortunately, we didn't have much speed up. I mean, it happened that a previous work was just very nice, so it achieved a very fast attack, even though it was human attack. And yeah, and for this cipher, we didn't have speed up because I think the reason was that we didn't have a nice linear correlation and linear approximation, and the LFSR, the size of LFSR is a bit large, so we didn't have nice speed up.
Okay, we can talk about it later. Any other question? If not, we can thank the speaker again.
Hello, can you hear me?
Okay, so the next presentation would be online, and the title is Quantum Circuits of AES with a low depth linear layer and a new structure. And it will be presented by Haotian Shi. Okay.
Hello? Hello, can you hear me?
I can hear you, you can go ahead.
Hello, can you hear me? And I'm sharing my screen.
We can hear you.
Okay, the screen, can you see the PowerPoint?
Yeah, screen is visible. The screen is visible. You can start your presentation.
Okay, thank you. I will give, hello everyone. Thanks for the introduction. I will give a presentation of our work named Quantum Circuits of AES with a low depth linear layer and a new structure. This is a joint work with Haotian Shi and Xiutao Feng. The presentation is divided into 4 parts. The first part is about the background. The second part is finding low depth signal circuits. The third part is our compressed pipeline structure. And the final part is about detailed quantum circuits of AES. First, the background. As we all know, recently, quantum computing has developed rapidly. Notably, Shor's algorithm has shown that a sufficiently large quantum computer can be devastating to many public key crypto systems in use today. Besides this, the secret key cryptography is also under threat. For example, Grover's algorithm can provide a quadratic speedup over the exhaustive search, and Simon's algorithm can provide an exponential speedup for finding the period of a 2-to-1 period function. Both of these 2 algorithms need the quantum oracle of the detected primitives. On the other hand, NIST has used the complexity of the quantum circuits of AES with the next steps to categorize the post-quantum public key schemes into different security levels. All of these reasons shows the importance to study the quantum implementation of many cryptographic building blocks, including AES. Of course, the synthesis and optimization of quantum circuits itself is an important problem in quantum computing. Due to the limited qubits and the phenomenon of decoherence, the circuit width, depths, T depths, and Toffoli depths should be as small as possible. Let's begin with some basics in quantum computation. A single qubit state is a unit vector with the basis states 0 and 1. Similarly, an n-qubit state is a unit vector with computational basis states described as an n-bit string of 0 and 1. The three fundamental quantum gates which compute classical vectorial Boolean functions are the X gate, C0 gate, and Toffoli gate. These three gates are actually the quantum equivalents of the classical NOT gate, XOR gate, and AND gate. One can say that these three gates act on the computational basis states like their corresponding classical gates. Actually, the Toffoli gate is a composite gate. It can be decomposed in several ways. For example, it can be decomposed with T depth 3 and 4 depth 9. Notably, the QN gate is often used to replace the Toffoli gate to reduce the cost. Since the QN gate has T depth 1 and only needs one ancillary qubit. The condition is that the target qubit must be 0. And the QN gate needs a measurement and has T depth 0. In this work, we consider two types of circuits. One is the encryption circuit, where the message and the key can be in a superposition state. The other one is the encryption oracle. Like in the classical case, the seed key is prefixed in the oracle, so the key register does not exist. A quantum circuit is a general notation of these two circuits. So let's move on to the second part, finding low-depth C0 circuits. In quantum computing, the optimization of C0 circuits is an important problem in quantum circuits. The status of C0 state is actually equivalent to the type 3 elementary matrix. As a result, actually the finding a C0 circuit of a matrix is equivalent to finding a matrix decomposition of this matrix, as described by the following theorem. Note that the permutation matrix can be seen as rewiring qubits for free. So a C0 circuit is actually a sequence of type 3 elementary matrices. This work considers the depth of C0 circuits. The quantum depth is actually the layers of quantum gates. In each layer, the quantum gates can act in parallel. These two figures shows two small examples of circuits. The first one have quantum depth 3. The second have quantum depth 2. Recently, there are typically two types of methods of optimizing the depth of C0 gates. The first one is computing the depth of existing circuits, especially the circuits provided in Xiang et al.'s method. The other kind of method is the greedy search methods, which are based on matrix decomposition. One of the few algorithms that takes the quantum depth into account is the Brugeri et al.'s greedy method. It is a cost minimization algorithm. That is, a cost function needs to be defined to guide the search. The operations must minimize the cost function. In the end, the algorithm will find some elementary row and column operations layer by layer, where each row layer and each column layer has depth 1. The decomposition form is like this. In practice, in the algorithm, each iteration, the column and the row operations are considered simultaneously, and each time a row layer and a column layer is generated, and so on. For the cost function, there are many choices, and the authors considered 4 choices of cost function to guide the optimization of the gate count and the depth. These 4 cost functions evaluate the cost roughly by sparsity of the matrix. So, these four cost functions reach their minimum when the matrix is a permutation matrix. As a result, they can somewhat guide the search. Our method is based on the Brugeri et al.'s greedy method and differs from it in some ways. We first observed that Their choice of cost function is not depth-oriented. Though not strict, the larger a row's Hamming weight, the more potential gains need to be done on this row or column. As a result, prioritizing the row or columns with larger Hamming weights might be a preferable choice to obtain lower circuit depth, which leads to the following cost function. It is based on the square of row's Hamming weight. Secondly, our cost function considers the row and column operations separately, and we add an additional judgment of whether a matrix can be implemented with depth 1 to better handle the sparse case. Here are some remarks. The time complexity of determining an operation to be done is O(n) squared, so this algorithm can be done in polynomial time. Note that it is a greedy algorithm. Note that the algorithm is suitable for small scale matrices and often fails into a local minima when n is larger. That is, the cost function will not go down. When n is larger, this case often comes. In practice, this algorithm is repeated thousands of times, and the best implementation is recorded. We first apply our algorithm on AES mixed columns. A recent record without ancillary qubits is step 16. We first apply WJV et al. Method and find a circuit with depth 12. Then using our method, we succeed to find a circuit with depth 10. This circuit can be used in the quantum circuits of AES to reduce the 4 depths. We also apply our method to many MDS matrices and matrices used in block ciphers. One can see that our method can find the best results for all of these matrices. Then I will introduce our compressed pipeline structure for the quantum circuit. For iterative building blocks like AES, there are many structures proposed to synthesize the quantum circuits. The auto-Blaze oracle of round function is a common choice. There are some structures based on this, including the pipeline structure, the zigzag structure, and the auto-place based round in-place structure. Relatively, the in-place oracle of a round function is relatively difficult to construct, and it's not the common choice. The straight line structure uses this. Furthermore, there is also related work of decomposing the oracle of round function. The shallowed pipeline structure delays the uncomputation of a round function to the next round to reduce the 4 depths. And there is also techniques about combining the computation and the uncomputation. We first introduce the structures based on the auto-place oracle. The pipeline structure actually computes intermediate states one by one. So it will have large width and the lowest round depths. The zigzag structure itself uncomputes some intermediate states occasionally, so it has lower width with a little bit increase in depth. The auto-place based round-in-place structure cleans intermediate states immediately after computing new states, so it has the lowest width and almost twice the depth of the pipeline structure. To combine the advantages of different structures, we propose a compressed pipeline structure. It works by computing the next intermediate state and clean the previous one in parallel. So the name compressed pipeline structure. It is a combination of the pipeline structure and the auto-place based round-in-place structure. One can see from the figure that the eliminating of Cj-1 is acted in parallel with computing Cj+1. So this is done in round depth 1, while in the auto-placed round-in-place structure, this is done with round depth 2. We then give a detailed comparison between these structures. Suppose the round function oracle has round depth 1 and needs alpha ancillary qubits. The state length is n, the number of rounds is r. The k schedule needs k qubits or k prime qubits. Our structure, it has the same round depth with the pipeline structure, and only needs 4 state registers, which is independent of the round number R. If the ancillary qubits of round function oracle is small enough, our structure will have a better depth-wise trade-off. Similar to the previous work, our structure can be used to construct the global oracle and the encryption oracle. For the global oracle, since a global oracle is almost 2 times the encryption circuit, one can refer to the above table. But for the encryption oracle, things are a little different. Since the round keys are prefixed, the remaining redundant states contains only R-1, which can be cleaned with much lower depth, with much lower cost with round depth 1. Based on this, we succeed to construct an encryption oracle with round depth R+1, which is almost half the previous record. The final part is quantum circuits of AES. The contents include 3 parts: quantum circuits of AES S-box, detailed quantum circuits of AES under our compressed pipeline structure, and improved encryption circuit of AES under the shallowed pipeline structure. First, the AES S-box and the circuit S-box. AES S-box, there are many types. For example, C2 circuit is the most common one, and the C1 circuit has a fewer cost since the target qubit can be 0. C3 circuits are actually serves the role of the inverse AES S-box. Here are some C1 circuits of AES S-box with low Y. On the other hand, note the notation, the circuit S-box. It actually computes some intermediate states. So it usually has low Toffoli depth and is used to construct low T-depth AES S-box. On the other, in another word, the AES S-box can be decomposed into S-box and on computation as sub-S dagger. Actually, in the shallowed pipeline structure, the sub-S dagger is delayed to the next run. That is, the on computation is delayed to the next run to reduce the fall depths. S-box and S-box dagger can be combined to save qubits. An important thing that is worthy to know is the circuit S-box. The input register of the circuit S-box may change to X prime before the on computation is done. So we gave a definition of input invariant S-box, which ensures that X prime is equal to X without using additional Toffoli gates. A simple observation shows that a sufficient condition of making an S-box circuit input invariant is that the qubits used to update the input register can only be further updated by CNOT gates. So just adding a reverse sequence of CNOT circuits, which are related to the updating of the input register, can make an S-box input invariant. One can see from the table that for the S-boxes which are not input invariant, by adding some CNOT gates can make them input invariant. Later, we will show that this technique can be used to reduce the circuit width in the shallowed pipeline structure. We then gave detailed encryption circuits of AES 128. For AES 192 and 256, the technique is similar. The hierarchy is like this. It is composed of beginning function B and the iteration function Fj. In the function Fj, the Cj-1 is cleaned by 16 C3 circuits, and in parallel, 16 C1 circuits are used to compute as Cj. So each round has round depth 1 and serves 32 S-boxes. The key schedule is a little bit different from the previous structures, since in our structure, 2 consecutive round keys should be able to be computed simultaneously by CNOT gates. In order to save qubits, we choose to store linear components of 2 consecutive round key registers. The dependency to compute is like this. So instead of using trivially 8 32-qubit registers, we only need 6 or 5 32-qubit registers. We give 2 key scheduled circuits, Kj and Kj prime. Kj is the universal case. It uses 6 32-qubit registers, and Kj prime uses the circuit S-box and S-box dagger. It only needs 5 32-qubit registers. We then gave a cost comparison of encryption circuits for different structures. One can see that our circuit only needs C1 circuits, and if the ancillary qubits of S-box is small enough, our circuit will have better depth-wise trade-off. Similarly, our encryption circuits can be used to construct an encryption oracle with lower T-depths. Previous researchers cannot break the limit of 2 times 10 layers of AES S-box. Under our compressed pipeline structure, we only need 10 plus 1 layers of AES S-box. The last layer is a clear function below. As a result, we succeed to construct an AES 128 encryption oracle with T-depths 33, while the previous best record is 60. The last part is our improved circuit for the shallowed pipeline structure. The problem is, as described earlier, if the S-box circuit is not input invariant, the input register will change before it is used later. So the input register need to be saved. For related works, the original work used input invariant S-box with larger width. They allocated 32 qubits for storing each Q3. Later in improved work, they use improved S-box, but the improved S-box is not input invariant. They allocated 10 times 32 qubits for storing all Q3. In our work, we observed that the S-box can be made input invariant, and by the K dependency below, we claim that no additional qubits need to be allocated for storing the input register. As a result, we succeed to synthesize an encryption circuit with a fewer width. Here is a cost comparison. Our improved shallowed pipeline circuit has the lowest total W cost, and for our circuit under the compressed pipeline structure, our circuit have a pretty good total W cost. It uses a low depth S-box and have much lower width. Finally, a conclusion. We first proposed an improved greedy algorithm for finding low depth signal circuits. We succeed to find an implementation of AES mixed columns with quantum depth 10. Then we propose a new compressed pipeline structure for iterative building blocks. It can be used to construct an encryption oracles with low round depths or T-depths. We further gave some improvements in terms of quantum circuits of AES, including detailed encryption circuits, low T-depth encryption oracles, and the input invariant S-box applied in the shallowed pipeline structure. This is all of our work, and it is worthy to note that there is a similar independent work by John et al. They obtained almost the same results as us, and it is a very interesting thing. Thank you, that's all.
Okay, thanks to speaker. Any question from the audience? Okay, no question. So I have one quick question that your greedy algorithm for finding the low depth CNOT circuit, so does it give really optimal result or it's approximate?
Let's move to this part.
Okay, so it improves the previous one, but I mean, it's not yet known whether it is the optimal, right? That's what you are saying.
Let me introduce the improvement. The previous works either optimize based on some classical circuits or or they use the matrix decomposition method, and their method is not depth oriented. Some researchers optimize the existing circuits. Our method, we try to use a depth-oriented search method, so we obtain a great improvement.
Okay. If there are no more questions, let's thank the speaker as well as all the speakers of this session.